our local ICE-CSIC institute with IEEC as well, Josep Miquel Girart and Mezcua, talking about galaxy mergers with the title of Magnetic Superhighways Discovered in Starburst Galaxies Winds. And I think as we are both local people, we don't need further introduction, so please go ahead, Josep.
Yeah, so thank you very much to all of you. As you can see, this is not a standard talk in the sense that first we have two speakers. In fact, we are three because Chema, you have to account that this presentation, Chema has been extremely involved. I think 80% of the slides are from him. So we thank Chema, even he could not be here today. And we have, you can see, you have two titles. The title of the paper we're presenting is the magnetic fields of the dusty nuclei and motor opposed, blah, blah, blah. And then the most marketing title is the magnetic superhighway discovered, right, by Starburst. This is the NRO press release titled in order to have more like a, to attract more the overall audience. And this is, as you can see, is an offer of two research groups in the institute doing completely different things, but we found in energies by using the millimeter facilities where the star formation group is expert with the knowledge of the extragalactic studies by Mezcua. And also we have a strong collaboration with the people in the IAI, the Instituto de Astrofísica de Andalucía. Okay, this is not the first time there is synergy between the different people. I think our group has already collaborated with Daniele Vigano, also the Exoplanet people, and then with high energy astrophysics with Nanda Rea and Francesco Cotti. So I encourage you to also find synergy with the different groups. And I also take advantage now that in 2 weeks, April 23rd, St. Jordi, there is the deadline of the ALMA. ALMA is the millimeter facility. So if you have any project that you think the millimeter wavelengths can be used to do some science, please contact us and we can see if we can find a common project. So we can help you to prepare a proposal. Okay, so with that, for the first part of the talk will be done by Mark. Okay.
Thank you. Yeah, so I'll start with a bit of background on galaxies, galaxy mergers, and why they are important. Because we think actually the galaxy mergers are key in galaxy evolution. And this is because during a merger, gravitational interactions can trigger inflows of gas to the center of the two merging galaxies. And this, in turn, can trigger a starburst, so increase the star formation in the two merging galaxies, and also can ignite the accretion into the supermassive black hole or the supermassive black holes in each of the two merging galaxies. Okay, so via galaxy mergers, we can trigger AGN activity. By triggering AGN activity, we can also increase the growth of the supermassive black holes. So galaxy mergers are thought to play a key role not only in galaxy evolution, but also in supermassive black hole evolution. And in addition to that, and as you maybe know a bit better, galaxy mergers can reshape the morphology of the galaxy. This is the most evident signature of a merger, as you can see, for instance, here. This is a very basic sketch of the process of merging of two spiral galaxies. I don't know, maybe if I use my mouse is better. We have a first early stage merger in which we see interaction. The two merging galaxies are already a bit distorted, are already starting to lose the initial shape. And in a second late stage merger process, we see that there's already only one galaxy, let's say, recognizable, but with lots of distortions, shells, tidal tails. Okay, so here the morphology is really reshaped. In this phase is when we have these inflows of gas to the center, triggering starburst activity and AGN activity. And we call this phase also ULIRG. And I'm going to go into ULIRG in the next slide. Okay. At this stage, there's a lot of obscuration. So the AGN might be there, but they are usually not detected because they are obscured. But when the gas is blown out, then we have a quasar phase in which the AGN or two AGN, depending on whether the black holes have merged or not, are visible. Okay, this is the quasar phase. Here we see still these tidal things, and after that, what happens is that the two spiral galaxies become one single elliptical galaxy. Here, the gas has been consumed, Typically, there's no star formation, and the AGN or the black hole is not actively accreting anymore. Maybe it's accreting at a low rate. Okay, so in this talk, we're going to focus on this late merger stage in which we have ULIRGs. ULIRGs are ultraluminous infrared galaxies, and we call them ultraluminous because the infrared luminosity can be above 10 to the 12 times the solar luminosity. Okay, so these are among the most luminous objects in the local universe. Actually, you can see here the spectral energy distribution of a ULIRG, which would be the blue line, compared to a starburst galaxy, a normal spiral galaxy, or even an elliptical galaxy. You see that across the infrared regime, the luminosity is way higher in the case of the ULIRG. This high infrared luminosity comes from dust that is heated either by the starburst or the AGN, as I said before, that is triggered during the merger. But as I said, this AGN is typically deeply obscure. Okay? And in general, ULIRGs are always or almost always the result of mergers, of ongoing mergers, in 90% of the cases. And you can see here images from Macarena Garcia Marin of some typical ULIRGs. You see clear tidal disruptions, shells, tails, indicative of a merger event. As I said, the gas funnel to the center can trigger starburst activity. We can have star formation rates of up to 1,000, between 100 and 1,000 solar masses per year. This is huge. This is very high. The AGN accretion is obscured, as I said before. So often, ULIRGs, local ULIRGs, are considered as analogs, local analogs of high redshift galaxies, star-forming galaxies, dusty star-forming galaxies. Now let's go to galaxies, but let's have a look at the magnetic fields, which are also very important. Typically, magnetic fields in galaxies are of the order of 5 to 15 microgauss, and try to memorize this number is important, okay? And they come in two flavors. On larger scales, they are usually ordered, and you can see here these yellow lines here. You can see how these magnetic fields follow, in general, the shape, the spiral shape of the galaxy. However, in the center, at small scales, the magnetic field is more turbulent, less ordered. And maybe you cannot see it here because of the colors, but it's a bit more turbulent. These magnetic fields are typically traced by, thank you, by either synchrotron emission, as is the case here. The synchrotron emission is shown as white contours, or Faraday rotation, or polarization mapping. And they are very important because they help regulate the star formation in the galaxy, the gas dynamics, and also the feedback. And we'll talk about feedback later. So magnetic fields are thought to play a key role in transporting cosmic rays and also metals across the interstellar medium of the galaxy. Now, what happens when we have a galaxy with magnetic fields that encounters another galaxy? So when we have galaxy mergers. Well, we think that magnetic fields are amplified due to the merger. This is because of the gas being compressed, and via shocks, the magnetic field is amplified. Also, there's an increase in the turbulence of the magnetic field. So while on larger scales, as I said before, you can see here that the magnetic fields, these lines, seem to follow the dust of the galaxy. At the center, there's no order. And in this case, it's probably because the magnetic fields here at the center are the remnant of the past merging galaxy, and also because of the AGN. Supermassive black hole at the center also induces some disorder or turbulence. There's an enhancement in the brightness, so the magnetic fields in mergers are brighter, are easier to detect. And actually, they can be amplified up to 100 microgauss. Remember before, I said 5 to 15. Now we are talking about 100. Okay? In the case of ULIRGs, merging galaxies like the ones we are presenting here. So in mergers, in galaxy mergers, magnetic fields are very important because they can help explain how the gas inflows to the center in the case of mergers of galaxies. They can also help explain the enhancement or suppression of star formation, although in general it's an enhancement in the case of ULIRGs and galaxy mergers. They can help understand jet and interstellar medium interactions because, as you know, jets, radio jets, are also formed thanks to magnetic fields. They can help transport cosmic rays and metals, as I said before, but also confine cosmic rays in compact starburst region. And I won't go into that, but they can also help explaining an infrared correlation that is typically found for this type of galaxies. Yet there are several open questions. One of them is how these magnetic fields are amplified in mergers. I said that thanks to a merger, we increase the brightness, we increase the magnetic field strength, but how this happens is not so clear. How these magnetic fields affect black hole growth, so the triggering of the AGN at the center is also unclear. In the case of ULIRGs, as I said, we can have ordered magnetic fields, maybe in the larger scales, but in the center, the magnetic fields are more turbulent. But it's unclear how this happens in ULIRGs, at which scales the magnetic fields go from ordered to turbulent. And also, which is the role that magnetic field plays in the feedback and the winds that we see in AGN and in galaxy mergers in general, as we will see for the case of ARC 2020, there are outflows, winds emitted at the center. So it's unclear which is the role that magnetic fields play there. So the case study to answer all these questions is ARC 220. This is the nearest ULIRG at a distance of only 78 megaparsecs. It's indeed a late stage measure as expected for ULIRG. We have two counter-rotating and highly obscured nuclei, a starburst nuclei. We don't know for sure if there are AGN or not because of obscuration. The separation is of around 1 parsec, more than 300 parsecs, and the total stellar mass of the system is nearly 10 to 11. The star formation rate, as expected in a ULIRG, is very high, more than 200 solar masses per year. And as I said, there are molecular outflows, very strong. Here you can see them in red and blue, but now Josep Miquel is going to tell you more about them. So ARC 220 is an ideal laboratory to investigate the magnetic fields and their role in feedback effects and the turbulent effects that occur in galaxy mergers. There were some studies already of the magnetic fields in ARC 220, but with a wide range of these fields estimates, you see from microgauss to tens of milligauss. So this is not really much constraint. Most of the emission, most of the detections came from synchrotron emission or major emission and was unresolved. So we don't know, or we did not know what was happening in the interstellar medium and in the molecular outflows, whether there was any link between the magnetic fields and the molecular outflows. So Miquel is going to explain the observations we have.
So in order to really understand the role of the magnetic field, we decided to go to ALMA. ALMA is a millimeter aperture synthesis telescope in Atacama, 5,000 meters. I think we already have given here several talks in the teacher seminar about ALMA, so I'm not going to go into detail. If you have questions about the ALMA, as I said before, the ALMA deadline is April 23rd, so you're still on time to submit a proposal. So what we decided to do is, because we are experts in polarization, as I will show you, is the most straightforward way to study the magnetic field. We decided to use band 7. Band 7, ALMA has different bands across the millimeter atmospheric windows. Band 7 basically covers the 300 gigahertz atmospheric window. So in wavelengths, it's about 800 micrometers. And we decided to do full polarization observations. So we can measure the total intensity, the linear polarization, and the circular polarization. We decided to set up the correlator in two spectral windows to study the dust continuum. I was using a large bandwidth as much as we could. That was 3.6 gigahertz. And then we also did simultaneously, we used two spectral windows to observe two molecular lines. One is the CO322, and the other one is a molecular ion, the HCO+43. Okay, with a goal to try to detect polarization both in continuum and linear polarization. Okay, the spectral line polarization was 4 kilometers, which for a ULIRG that's good enough because the lines are usually hundreds of kilometers wide. Okay, the spatial resolution, which is very important, was set up 0.24, which is 96 parsecs to resolve the two nuclei in the merger. Okay, so we can really study the magnetic field independently. Okay. Okay. So the approach was to study magnetic fields using polarization in a dual approach. Okay. The first is use dust continuum to through detecting the linear polarization to try to study the magnetic field. How does it work? Okay. Which is the idea behind? So in the interstellar medium, we have gas and dust particles. Okay. In the molecular regime of the interstellar medium, the dust is a major component of the mass budget in the clouds. Okay, and these particles usually are not spherical; they have some elongation. Okay, and these particles usually have some paramagnetic and ferromagnetic components, and that means that they are sensitive to the interstellar magnetic field. Okay, and if they are not spherical, what happens is they tend to be aligned with the magnetic field with the minor axis parallel to the magnetic field. Okay, and this is a very simplistic sketch of what happens for this is for a Polarized type of grains. Okay, and the theory behind how this happens, this microphysics to align the grains, is really sophisticated and difficult to understand. Is the Redditor alignment by Lazarian et al. But it works, and we know from the 50s that the dust particles are aligned with the magnetic field and produce linear polarization. So in this sketch, what we have, assume that we have a uniform magnetic field with the grains aligned with the magnetic field with minor axis parallel to the magnetic field. You have a unpolarized source that on the background, and it crosses the cloud. If it crosses the cloud, because you have the grains aligned with perpendicular to the magnetic field, what you will produce a linear polarization. Some linear polarization where the position angle will be parallel to the magnetic field. Okay. Now we can think of the reverse, and these dust particles, they behave as a black body, a gray body, to be more specific. So they are going to emit radiation, and because they are elongated with the magnetic field, this radiation is going to be also partially linearly polarized with a polarization angle perpendicular to the magnetic field. So if you have a telescope that is sensitive to the linear polarization, we can detect the projection of the magnetic field on the plane of the sky. And from here derive the magnetic field properties. So that's the first technique. The second technique, and we can do it simultaneously with the ALMA, is to observe the linear polarization in the molecular line. In the case of the molecular lines, when you have a magnetic field, even if it's small, the lines are going to split into magnetic levels. Okay, I'm not going to spend too much time, otherwise I could spend here for all. But what happens is these two magnetic levels are basically proportional to the magnetic field and the properties of quantum properties of the molecule. Okay, so the stronger the magnetic field, the splitting in frequency is larger. So ideally, if you have an extremely high magnetic field, you could see the submagnetic levels at different frequencies. But it doesn't happen. It's because the magnetic field in the interstellar medium, as Mark said, is extremely small, of the order of 10 microbars. So this splitting is very small, and it's much smaller than the line width. Okay, so the only way to detect the linear the different levels is through two mechanisms. The Zeeman effect basically is circular polarization that gives you the line of sight magnetic field strength. Okay, and the other is the Goldrich-Pilafis effect. Goldrich-Pilafis effect is a linear polarization that arises from molecular line emission when there is an anisotropy in the population of the submagnetic levels. And this anisotropy in the population can be done because you have large velocity gradients or anisotropic source of radiation. Okay, and then you have a linear polarization of the lines that can be parallel or perpendicular to the magnetic field. So by using the Goldrich-Pilafis effect, we have an ambiguity of 90 degrees. We don't know a priori unless we have extra information on the physical source of radiation. Okay. So this dual approach, with that, we will be able to study the magnetic field from the dust and the magnetic fields from the CO lines. Okay, so that will give us an extra information how to which are the physical properties in the region we want to observe. And indeed, many, many years ago, we used this kind of dual approach, okay, to study the magnetic fields in a star-forming region. This is the second paper using an aperture synthesis millimeter telescope to observe the polarization in a star-forming region. And in this case, we use the dust continuum, which is the gray scale here, to measure the linear polarization, which are these white segments, is giving you the position angle of the dust polarization. If you flip it 90 degrees, you see the magnetic field on the dust continuum. The dust continuum is tracing the core that is in falling toward the protostars because of the gravitational force. Okay. And in addition, in this case, we also detected the polarization from the CO221 line. Okay. The CO221 is not tracing the core that is accreting, that is in falling toward the protostar, but is tracing the outflow, the bipolar outflow. Okay, so this is the effect of the magnetic field, the magnetic braking. We basically remove angular momentum and creates a jet perpendicular to the disk. Okay, and we see clearly the outflow from the CO in the reshifted and reshifted, and we found that this outflow the emission is polarized. Okay, so we could combine these two polarization mechanisms, dust and molecular lines, to really better understand the role of the magnetic field. In this case, we found that the magnetic field in the core is parallel to the outflow. Okay, so that means there is a physical relation between the magnetic field that is being dragged between the collapse and the production of the outflows. Okay, now we have studied with more detail this sort. With ALMA, we were able to do a 3D picture of the magnetic field, and this is a paper just was accepted this week and is going to appear in Nature Communications. Okay, that will be for another pizza seminar. Okay, so this is the result. Okay, so what you can see here is the color scale. Okay, in the two cases is the dust continuum at 300 gigahertz, 350 gigahertz from ALMA, and you can see the two nuclei, okay, east and west. Okay, so this is the dust continuum. Okay, so it's tracing the molecular content. The molecular content is probably is the coldest part in the nuclei. Okay, and then here you see this green dash contour. This is the linearly polarized the polarization, the linear polarization of the dust emission. So we see polarization in the two nuclei. Okay, and the segments. Okay, here this black segment is tracing the magnetic field. We already have flipped the position angle of the linear polarization by 90 degrees to trace the projected magnetic field in the plane of the sky. Okay, so you can see the two nuclei are polarized. Okay, but they have quite different behavior. Okay, in this case, in the nuclear to the west, the polarization basically is unresolved, and it has a direction in the north-south. Then we see some extended emission here, and in the east core we have a lot of superstructure. I'm going to talk about that. Okay. The other properties what we found is when you do a polarization observation with ALMA, typically you get like a 2, 3%, 4% in molecular cores in star-forming regions in our galaxy. The values we obtain in this merger are much, much smaller. They are almost at the limit of detection. It's 0.2 for the west core and 0.4% which is a really, really tiny value of the polarization. That means in order to detect that, we really needed a lot of integration time with ALMA, but ALMA is very sensitive. So that's not a problem. In addition, okay, and let me show what I think Mark already talked. Here we have again in color scale the dust emission from the two cores, the two nuclei, and then here you have this redshifted and blue shifted contours, which is tracing the the extremely high velocity component of the CO, which is tracing the bipolar outflow gas that is being ejected due to magnetic braking. Magnetic braking is the main mechanism to remove angular momentum, so the gas can keep collapsing toward the center. And we see these two bipolar outflows in the CO, okay, at very high velocities. So if you go back to the low mass case I was showing here, you see it's exactly the same picture. You have a core that is collapsing, and in this case traced by the dust, and you have a bipolar outflow which is the consequence of magnetic braking. But these are scales of few hundred U. Now we're talking about masses of one solar mass. In this case, we're talking about mergers, the nuclei of an merger. So these are completely extreme cases. Here, the physics are much more extreme. But we see the same phenomena: an outflow and a core that's probably collapsing. Okay? And in addition to that, for the two outflows, in the west outflow, and this is a spectrum, okay, for the east, which is this one, and the west is this one. In this case, these are the outflows. The red and blue is the bipolar outflow. In the west outflow, we detect the linear polarization. It's very weak, but we detect it, okay, thanks to the ALMA sensitivity. And here, here, these segments, blue and red segment, is the magnetic field associated with the outflow emission, the CO. So this is, again, is kind of a parallel result as the one we obtained like 30 years ago, but in a merger, which is, I think, is extremely interesting. And these outputs are very high velocities, more than 500 kilometers per second. Okay, so this is the picture you already saw. So in this case, what we are showing here is not the dust continuum. Okay, just to see how different it is from a galactic star formation. These two color scales is image obtained with a very large rate of 33 gigahertz, and this is synchrotron emission. Okay, so you have the extremely hot, ionized, magnetized plasma, and then surrounding that there is the shell of the molecular gas, which is what's called an probably similar density. Okay? But just to illustrate, because this is high angle resolution, and what we can see here is that in the east nuclei, the emission, the nuclei has kind of a elongated structure, kind of a disc-like structure, and the magnetic field is having like a kind of a spiral pattern. Okay? So that means in this case, when we can resolve the magnetic field, probably this spiral pattern is probably telling you that the angular momentum is producing this rotation of the magnetic field. Okay, so this is an effect of that this nuclei is rotating, and then the magnetic field lines are being dragged by rotation, okay, which will create some tension at some scales. It will probably produce the magnetic braking, which launches the output. Okay. However, in the other one, the magnetic field from the dust is not resolved, so we don't know which is the structure, but we know it's in the north-south direction, and this is parallel to the outflow. And in addition, in the redshifted outflow, the magnetic field is also parallel. So there is a connection, physical connection between the envelope, which a magnetic field, and the outflow magnetic field. So that means the magnetic field in the two systems are related. So it means that the magnetic field is probably having a role in launching these molecular outflows. Okay. And then the other structure we see is this. It was not expected. This uniform magnetic field, and as Mark told us, here the supernovas, because you have a lot of supernovas injecting a lot of energy, we'll expect a very turbulent magnetic field. But in this case, we see a lot of a relatively uniform magnetic field, and we think this is tracing a bridge that connects gas between the two nuclei. So it will be interesting in the future to understand better this bridge. The low polarization fraction we see, because we see a very small, this is probably a product of the turbulence. So if you have magnetic field that have a uniform component, a turbulent component, I mean, what we are also observing is the projection on the plane of the sky. So if you have a turbulence component which is significant in the line of sight, you're going to smear out the magnetic field, because the magnetic field what we see is linear polarization. And linear polarization we detected through Stokes Q and U, which could be positive and negative. So you have a lot of superstructure in the line of sight. The different superstructures in different directions are going to cancel out. And this is what produces the polarization fraction is extremely low. Okay, so this is probably a consequence of the presence of a significant amount of turbulence in the kinetic energy of the system. Okay, so we're going back here. So yes, and in the bridge, the polarization fraction is quite high, 5%, and again, this probably is indicating in this kind of bridge this kind of, I don't know, a streamer, a strongly magnetized streamer, where turbulence is not so important. We detect like a 3 to 5%. And these are the typical values we detect in the galactic star-forming cores. So then we did some energetics to see whether this magnetic field, which is the role in this process of merging. Okay. So with that, and this was done by Enrique, which is the expertise of this kind of systems. For me, it's a bit out of my expertise, but we get values that are, for me, look very reasonable. So he did several methods. So one is basically assuming, you just assume that the kinetic energy, that means the total kinetic energy, is in a correlation with the magnetic field energy. Okay, and with that, you can basically you have this equation, and you can measure which will be the magnetic field strength in order to achieve this assumption. It will be few more. So this is like a 2 orders of magnitude higher than the expected interstellar magnetic field in regular spiral galaxies. Okay. When we use the technique of the Davis-Chandrasekhar Fermi, this is a very old technique based on the dispersion of the angles. And from here we also get similar values, a bit larger, a factor 2, but of the order of several milligauss. Okay. And then we also calculated, and this was done in das continuum, but because we have also data in the CO, we can apply a modified Davis-Chandrasekhar Fermi that is already taking into account the specific of the outflows. And here we get again, within a factor of 3 or 4 similar magnetic field strengths. Okay. To me, to see this difference is not significant. We know these methods have some uncertainties. Usually, the uncertainties usually is a factor of 2 at best. So if you see changes in a factor 2, you are happy in all cases. And we see. And the important thing is this is like a several order of magnitude higher than the expected magnetic field in the spiral galaxies, at least in the disk of the galaxy. Okay. And then we compare that from the literature, and we see that there is a lot of values, but the thing is these are obtained with, in most cases, with apertures or with angular resolution much larger. Okay. Only the masons, with masons usually are coming from very, very localized positions, so they are not affected by the line of sight averaging, are the ones that are more in agreement with our values. So and then we did a calculation, assuming that the star formation efficiency is similar to the typical starburst galaxies. There is a relation from other studies where they relate the magnetic field strength in these starburst galaxies with the star formation rate, and they found this kind of correlation, and we try to extrapolate this with the values we have in the R220. And we found, oh, is it okay? Hopefully, yes. Okay, so we found that extrapolating the typical relation between magnetic field star formation rate in the starburst, we are getting magnetic fields that are significantly smaller than we are obtaining observation. Okay, so as Amar suggested, the effect of amplification, of magnetic field amplification during the merger is really significant. This is probably because of the compression of the gas and the presence of supernova that is also producing a lot of kinetic energy and compressing a lot of the gas, both the ionized and the molecular cold component. Okay, so as I said before, so what we found is amplification, a clear case of amplification that was expected, but now we have more quantitative numbers. Okay, we found that the kinetic energy is in the outflows is very important. What else? The alignment between the magnetic field and the outflow in the west core, this is very important. So that means the magnetic field are playing a role in ejecting these outflows, and these outflows are strongly magnetized. And if they are strongly magnetized, cosmic rays are charges. So they're going to be coupled with the magnetic field. So that means that these outflows, these magnetized outflows, are responsible to at least focusing these cosmic rays and metals to the intergalactic medium. So these outflows that are produced, these IGNs, are probably ejecting a lot of enriching intergalactic medium through this outflow. And this is a very important result. So this is why the press release, we call it they decided to title the press release as magnetic highways. Okay, these outflows are magnetized, and is a way to really put a lot of metals and cosmic rays to the coming from the nuclear to the intergalactic medium. Okay. And these are the conclusions. I don't want to feel, but I think it's okay. So as a conclusion, well, this is the first detection of polarization in the CO322 with ALMA. I mean, there has been other detection, but not for this transition. I think the CO221 was already detected, but not in a merger for the SMA in Starburst galaxies, but on much larger scales because SMA doesn't have the sensitivity and angular resolution than ALMA. But at least at the nuclear level, this is the first detection of the CO polarization, and that help us a lot to understand the connection between the magnetic fields and the production of the outflows. And as a future work, for example, we found this dust bridge, which is highly polarized, and we cannot resolve that. So we call it dust bridge, but that has to be confirmed, which is the role in this merging. So now we are planning to do new observation with ALMA, basically going to higher resolution, because as I told you, in the West, nuclear, basically the dust polarization is unresolved. So we cannot really see the superstructure. So we need higher resolution to confirm the association of the outflow magnetic field with the core. And as an anecdote, of course, being a press release by the NRO, this news went to different countries. Okay, and one of the most, I think, interesting response was this one. So someone used AI using the title and decided to put this picture of the magnetic highways. I don't know if this one knows Hindu, but you can see here ALMA R220, and you see highways with a funny. You can still see that in the web if you look for that. And with that, I think it's all. Thank you.
Okay. Thank you for both of our speakers. Does anybody have any questions? We have plenty of time. Very golden time.
Of energy, we haven't really. We'll have to check if we did. I don't think we did. But this outflows, I mean, we are not the first ones to detect these people outflows. There was already some other papers that already did that, and I guess in there they have probably have done the estimation of the kinetic energy in these outflows and compare with the overall energy budget in this merger. Yeah, but this probably has in the ICE has done in the. So I cannot give you a number. I don't quite understand which component you are referring to the dust bridge. Yeah, well, this is, the dust bridge is kind of, is this here. I mean, we see kind of clear extension of the dust emission, so it's not so clear. So it's basically the fact that we see a linear polarization that is much higher than in the center, okay? So that's probably from some organized magnetic field. And because it's in this direction, we think this is kind of a bridge that connects the two. But we have to, of course, we have first kinematically confirm that and then resolve that. That's why we are trying to go to higher resolution to really see if this is a bridge. And this is a bit of speculation.
You said that the kinetic energy involved in turbulence is very important, right? So I wonder, how do you reconcile this with the flux freezing to build the bridge, or it comes from a different part of the?
In the bridge probably comes from a different. I mean, this turbulence probably is happening more in the core. We have a lot of star formation activity, a lot of supernovas, and probably the physical conditions in the bridge, which is probably a bit more not as energetic as within the nuclei. We,
to quantify the turbulence?
we don't know. In the bridge, we don't know because to quantify the turbulence, you need the kinetic energy. I mean, linear observations of molecules, right? To do like kinematic studies. And for the CO problem here, I mean, for the high velocity, we are sure that we are probably in the optically thin or partially thin regime. But once you go to the core velocities, the galaxy velocities, the CO is completely optically thick. So tracing kinematics of a possible bridge in between, that will be very difficult. So we will have to explore other like isotopes of CO or other denser traces where they trace better probably the kinematics, and there you can measure the effect of the turbulence.
I think here it could be like what I showed for Centaurus A, that this bridge is still, so this magnetic field is still the remnant from the previous galaxy, right? That this hasn't been affected by this turbulence that affects more the cores.
Okay.
It can also be that.
Yeah.
I haven't seen.
I haven't seen that before. Okay.
Yeah, thanks for the talks. I'm wondering, of course, you focused on this object, which is the nearest and the easiest to observe. I'm trying to understand how general your conclusions are. So is this something you expect to find in general in all these mergers? Is this something unique to this system?
Well, yeah, of course, with an object, statistics is, but you assume that this is that, the overall properties of this merger, and you can correct me, are probably very similar to other ULIRGs, where you have also merging galaxies. So I don't know why this, by studying something that has not been explored in other galaxies, but the rest of the properties are the same, for me, the same. In fact, now we're trying to do like a follow-up in other mergers to see if we can see the same effect. The problem is being the closest is the brightest. If we go to other sample, that will be, I mean, if we here we did like 10 hours with ALMA, with like a 30, 40, and it starts to become like a prohibitive to get so much time. But yes, the idea be at least a couple of more mergers will be nice to see. We see the same effects. Also, this is a time evolution, right? So it depends at which stages of the merger you are seeing the merger. Probably the magnetic field property is going to change a lot from the. I mean, the original merger you have probably tens of microgauss, and when you have a late merger, you expect this kind of amplification. So you have to select candidates that are similar to this to see if the same properties.
I think, and also you said the number now I was going to ask, you mentioned that 5 to 15 microgauss, this is the typical, and this enhancement is a factor of 1,000 or so.
Yeah.
That's the.
I mean, you already expect some enhancement because of the density increase at this, but it's larger than you would expect. As we show by extrapolating the magnetic field, you would expect if this is just a regular starburst galaxy. Yeah, Tony.
Yeah. This doesn't include Zeeman splitting, right?
No, well, but
what are the prospects for Zeeman splitting measurements?
With a 500 kilometer line, 0.
Okay.
Because the splitting, you need very narrow lines too, because this is the derivative, right, of the Zeeman split is the derivative of the total intensity. When you have a very broad, smooth spectral lines, unless you have kilogauss, then with kilogauss, I'm sure you can see it, but with milligauss, no.
Yeah.
Not even with milligauss in the star forming region that are more quiescent with spectral narrow lines, we still have very, very difficult to detect that. In fact, with ALMA, there is no detection.
Yeah.
Maybe at last.
Not sure. We'll have to get there.
Yeah, Alvaro.
I think there's been a question there for quite some time.
Yeah.
Yeah, so just to clarify some of them, most of the questions I had, so they were asked. Thanks to both of you for the talk. Two things. One is when you were in the table, you were reporting the magnetic fields for the blue shift, red shifted. This is for the outflow loss, or do you
Yeah.
magnetic field in the core?
Well, we did it both. We did the standard this year, the Davis and Checa for the dust continuum in the west, in the east, because in the west is unresolved, so you don't have statistics. But in the outflow, especially in the redshifted, you have enough. I mean, you have to be a bit careful because we don't have huge statistics. We are talking about statistics with 6, 8 independent numbers, right? So,
the course of the values because of the of few milligrams.
yeah,
Compared to the other.
milligauss, you mean?
Yeah, I don't know what I said here.
Yeah, yeah. So it's comparable, which I expect that because they are almost physically coeval, right? I mean, coming from similar scales. I mean, of course, we need the angular resolution to resolve that and really say that with confidence.
The other question that I had was connected to the bridge that there have been many questions of. Is there any hint that such a bridge exists? Maybe in infrared images or in optical images or something?
No, in optical, forget it because this is obscure. I don't know. I mean, if this is cold gas, you will not see it in the near infrared.
I wonder if there is some kind of extinction. You could see some kind of like this infrared dark analysis.
Yeah, I think the only way is going to the dust and trying to resolve the circumnuclear region from the nuclear. So you can really confirm the presence of this bridge associated with this kind of uniform magnetic field.
And integrating deeper here with ALMA, would we reach the sensitivity required to detect this bridge?
You don't have the angular resolution, so you can go deeper at the same angular resolution, but we will not going to resolve because the nucleus are so bright that basically you see like a small, in the emission you see here something, but it's not. I mean, you need to resolve that if this is a real bridge or not. I will not say anything. We need the angular resolution to really resolve any dust structure around the nuclei.
Continue with this question. Why don't you observe a radio frequency, for instance, in 6 centimeter polarization from the gas to the bridge?
Well, we don't know if the bridge is pure molecular content or not. I will expect to be probably more like a colder phase than in the nuclear, where you really know we know that we have synchrotron radiation at the smaller scales.
My question would be more what you said, not about the theory of the broad domain field being either favoring or inhibiting propagation of the subject. You said that in the outskirts, it's more aligned with variable usually, and it's more disorganized in the center, and that in some cases favors sometimes some cases inhibit them. I didn't understand really the difference between the level of magnetic field organization and the pressure it had on either favoring or inhibiting propagation.
I think it can help because it can help compress the gas, and this can trigger the star formation. And this happens more at the center where you have gas inflows, and the magnetic fields are not so ordered as in the. Maybe you can go back to the initial images I showed.
Yeah.
Where we had.
This one?
No, in my part, like yeah, maybe here. Yeah, maybe here, or even the next one. Yeah, here. So in principle, here in the outer parts, this is also a merger. What this is Sun A, and this was also a merger. In the outer parts, at the larger scales, the fields are still quite ordered. But here at the center is where we have the inflows of gas due to the merger itself, but then also more turbulence. And I don't know why, but if this can compress the gas, it can trigger. There's more gas, and the gas can be compressed, so there's more star formation going on. I don't know the detailed physics of how this can happen.
Well, at some point you need like an ideal effects because the magnetic field also suppress star formations. You need some effects of dissipation of the magnetic field to allow that acquitting, right? So yeah, so that's yeah.
And here is where I said also that for this object, there's a bit of still being at the center where there's more chaos, but there are still some order in the magnetic field, and this is where they said that this can be remnant of the previous two galaxies, so the previous before the merge.
Any other questions still remaining?
There is here. Oh, yes. Okay.
Oh, okay, one more.
So do you see evidence of shock in this temperature and in studies contribution to light of the shock properties?
Shocks can also compress the gas. We don't see shocks here. We haven't investigated that. But this is another way. Yes. Yeah, shocks.
Like with James Webb, for example, that people try to change the probability and relate that of the ray,
We need to investigate shocks.
investigating the infrared emission with James Webb, confirm shock properties of the ray. Is that something possible?
I'm sure it's probably very bright in the infrared, right? So James Webb probably, I'm sure there is already James Webb observations, and then you can use like these tracers of shocks, like iron, H2, yeah. But I think these two nuclei, the scales are so small that when you James Webb, you may see the tracers, but you may not resolve the shocks.
Sorry, the separation was like this 1 arc between the nuclei, and James Webb is super, but it doesn't really resolve much below that. So
Okay. I don't see any more questions, and we already had plenty. So let's thank both speakers again. And as usual, please wait for the speakers to arrive before you start eating the pizzas.
Sí, muy azúcar. No, yo voy a sortir, otra cosa va a sortir ya un par de meses. No, la sortilla fa, sí. Y yo,